Hello and welcome to the online info session about the Energy Lab 2.0 at KIT, a platform for research on future energy grids, energy storage and synthetic fuels. My name is Martina Waldner and I am Senior Program Consultant at HECTOR School, the Technology Business School of the KIT. So what's on the agenda tonight? So after a few words on the KIT and HECTOR School, I will hand over to Professor Dittmeyer for opening the door to the Energy Lab to us. So the session here will be recorded, and also to let you know, if you have any questions, feel free to type them into the chat window. We will answer the questions after the presentation. Beforehand, I already received some questions and they will also be answered at the end of the session as well. So welcome to KIT. The Karlsruhe Institute of Technology is one of Germany's universities of excellence. Further, the KIT is the research university in the Helmholtz Association and has the goal to create and impart knowledge for the society and the environment. It is the objective of the KIT to make significant contributions to the global challenges in the field of energy, mobility, and information. Within these three fields, all the further education and the master programs at HECTOR School are also located. So what is HECTOR School? HECTOR School is the technology business school of the KIT and offers trainings to transfer the technology know-how from KIT directly into industry. Therefore, all the programs at HECTOR School have access to the extensive research resources like laboratories at the institutes at KIT. And through this, we can really meet the demand to incorporate the latest research results into the teaching content. So next to working, you can update your know-how, your skills of yourself and of your team, and stay on pulse of the time and gain further knowledge. So through this HECTOR School, I can really say enables professionals to pursue exciting careers, and we are very happy to be a strategic partner for the HR departments in all industries worldwide, and here especially in the field of recruiting, retention, and requalification. The basis of all the trainings at HECTOR School are the 6 master programs. So let me see to move to the next slide. Yes, so here we have the basis. It's our 6 master programs, and they are ranging from product development, mobility, production, of course, energy and digitalization. And especially the Master in Energy Engineering and Management prepares participants to guide their company to follow the Green Deal and, for example, how to implement a sustainable energy system. Because it is really essential to make, when you make sound decisions, that participants and future leaders who are taking part in this course receive the necessary know-how in this Master in Energy Engineering and Management. And there, for example, you will learn how hydrogen technologies have an essential role now in facing the climate challenge, and also in all aspects. So hydrogen, not just in mobility, but in industry overall. And then during your master's, you will also get in touch with the Energy Lab. And today I'm very thankful to Professor Dittmeyer that he is introducing the Energy Lab 2.0 at KIT in detail to us. So a few words on Professor Dittmeyer before I hand over. Professor Dittmeyer started his chemical engineering career at the Friedrich Alexander University in Erlangen-Nuremberg, and he also obtained his PhD in habilitation there. At DECHEMA, this is the Society for Chemical Engineering and Biotechnology. He was head of the Department for Chemical Process Engineering. And since 2009, Professor Dittmeyer is full professor at KIT and director of the Institute for Microprocess Engineering. So his research focus is on microprocess engineering, catalytic reaction engineering, but also what we are strongly having a look at today here, chemical engineering storage and the conversion of renewable into gas, synthetic fuels and chemicals. So next to many other obligations since 2014, Professor Dittmeyer is project leader in this large Helmholtz large-scale infrastructure project, the Energy Lab. And with this, I want to hand over to Professor Dittmeyer. I'm very happy that you are with us today, and I look very much forward to your insights about the Energy Lab at KIT. So, and please unmute yourself, Professor Dittmeyer.
Very good. Thank you. Thank you very much for the introduction. I think your presentation still is not in presentation mode. At least I see.
Yeah, this is definitely true that we are here, that I have to change this so that everybody gets the full. My screen is just a little bit blocked here, so I have to see. So let me just, I have to close some other windows. So. So, okay, now, so I'm gonna speed up and go through again so that we are reaching your slides. So unfortunately, my laptop. So, but now here we go.
Well, thank you very much. Welcome everybody here to this talk. It's a pleasure for me to explain to you this nice infrastructure that we have here for research on future energy systems. Basically connecting the electrical part of the system, so the power grid, with the chemical part of the system, which is the storage in chemical energy carriers and then also the synthetic fuels. Can I have the next slide, please? So that's my agenda, the outline for this talk. I will briefly touch the climate crisis, remind you of the national targets we have regarding CO2 emission reductions, and then basically concentrate on the different topics in the Energy Lab, which is the Smart Energy System Simulation and Control Center. That's the electrical and information technology part, and then energy storage, power to X, and the outlook. Climate crisis, you are aware of that. Basically, this picture here tells you all. It's getting warmer and we are to blame. That's the essential facts we have to consider here. So please, next slide. And it's also clear that we already know that for a while. So I collected the important points in time here. So in fact, already in 1824, people knew that there is an influence of the atmosphere on global temperature. And already in 1965, the American president was warned by his scientific committee, by his advisors, that we will run into trouble. But not much happened since then. Despite different conferences on climate change, you can say, or we have to confess that really after the public demonstrations, things started to move. That's a matter of fact. So please, next slide. And on that slide, I'm summarizing the situation and the targets we have. On the left, in this chart, you see the greenhouse gas emissions in Germany, according to the different sectors like energy, industry, buildings, transportation, agriculture, and then waste management and other. And in the middle, you have the same representation for the year 2020. The numbers are, of course, in million tons per year. And there you can see that we made some progress until 2020. And if you look more in detail, if you want to see more in detail, you look on this square where you have the years. And there you can see that the last 3 years we were on track. We had significant reductions. The last year, of course, it was due to Corona. And now we are again moving back to higher emissions. That's the number for 2021, which we have above this middle chart. You also know that with the climate protection law, we have sharpened the goals. We have fixed clear targets for the individual sectors as well. We want to have minus 65% emission by 2030, and then further down to minus 88 by 2040, to 0 by 2045, and then below 0. That means we have to take really quick and far-reaching action in all sectors, not only in the electrical sector. And if we go to the next slide, we see the share of energy products in total final energy consumption. And what is shown is electricity. So how much of the overall final end energy is electricity in the different countries in Europe. And you see here that not much is actually electricity. Most of the energy we consume as fuels, as heat, and not as electricity. So even if we then have the power sector CO2 neutral, there is still the other sectors. So this clearly tells you that it's important to not only focus on the electrical side of the problem. So next slide, please. And that still it's the case that renewable power, renewable electrical energy, mainly from wind and solar, nowadays is the most attractive option as primary energy, because it's the cheapest way how you can generate power. And if we have this vision that in the future we will base our overall energy system on renewables, but on the side of the end energy, we need more than electrical energy. We also need fuels and heat. That already brings about the concept of power to X, of converting renewable electrical energy into chemical energy or heat. And on the right side, I've listed the 3 basic reasons why we need power to X. One is for this rapid and deep defossilization of the sectors which are very difficult to electrify. And that mainly holds for transport and industry. And the second point is that we also have to store energy because of the intermittent nature of solar and wind energy. So we don't have it at all times. We only have it when the conditions are good. But we also need power when there is no wind and no sun. So we have to store for longer periods of time as well. And that works better in chemical energy carriers. And the last point is that we know that we cannot generate all the energy we need in Germany within the borders of Germany. We will also in the future rely on the import of energy. And that usually also works better in chemical energy carriers, with chemical energy carriers, than with electrical energy. So for these 3 main reasons, we need power to X. And power to X means you produce hydrogen, and then the hydrogen can be further converted into products such as methane, liquid hydrocarbons, or maybe these oxymethylene ethers or methanol, which are future fuels. And in that way, we can still match all the different needs we have in our society. So next slide, please. And this brings us to the Energy Lab, because that's the arena where Energy Lab works. What is the Energy Lab? It's a large-scale infrastructure for R&D on the important components and how they function together of the future energy system, which certainly is a smart energy system, and it's based on renewables. it has experimental plants, and it has a powerful simulation environment to establish virtual platform for energy research. And on the experimental side, we have modular plants which allow us to validate new energy technologies, let's say, in a semi-technical environment. Next slide, please. And with this infrastructure, we then focus on questions like demonstration of storage technologies integrated with electricity generation and energy consumption, the transition to a more flexible electricity generation, both with regard to load and to fuel. Also the cross-linking of the different grids, power grid, heat grid, gas grid, and the integration of storage. That's the electrochemical storage, but also the chemical and the thermal storage into that system. And the last point is how we couple these power and other energy grids with an information network that then allows us to have safety and to handle the large amounts of data, and also privacy of the data that you have in this system. So that's the research objectives. And now we look into the different components. This is actually a photo of this nice building, which has the Smart Energy System Simulation and Control Center. We call that SENSIC in short. And there we have 4 labs. They are shown here. And then you have these model houses behind the big hall, which is called Living Lab Energy Campus. And there we have these experimental buildings, which have different energy technologies inside, and where we look at how this behaves over the day in typical user in typical use, and which implication this has for the grid and for the people in there. And now we look into the 4 different labs a bit. Next slide, please. The first one is the Control, Monitoring and Visualization Center. There we study new concepts and develop new software for control of such smart energy systems. We can do energy system monitoring. We can do visualization. You see that on the picture illustrated with this big screen. You can look at the power grid, the heat grid, the gas grid, the energy storage, and all different things. Next slide, please. And one highlight here, what the colleagues are doing is they developed an open software platform, which allows you to study or to operate such smart areas, and also to optimize the operation of such smart areas. And it's made in a way that it allows you to implement a lot of existing third-party tools. And you can also design such networks and areas. And so this is one highlight of the research people are doing in this lab. Next slide, please. The next lab here is the Energy Grids Simulation and Analysis Lab. There we look at the design, operation, and digitization of future energy grids. And this involves hardware and software infrastructure, and then the modeling. And what we look at is both microgrids. You see a few examples here. In the middle, you see a picture of the campus north here at KIT. So that's a microgrid, if you want. It's an island network. Could also be an industrial site. That's one level where we look at, which we look at. And on the right side, you see Germany, a map of Germany with the different grids, and also Europe. So this is the other level, which is investigated with all the different grids you have there. And on the next slide, I give you one example. That's a real-time simulation then, which we can do of our campus north. You can basically click on different buildings. You can see what happens in those buildings regarding energy consumption. You can also see the history of heat consumption, power consumption of these buildings. And then, yeah, that allows you to observe and to simulate this whole campus in real time. Next slide, please. Then we have the Smart Energy System Control Lab. There, the focus is on how you can guarantee that the power grid quality is fulfilled so that you always have the right frequency, the right voltage, of course. And that shows you the facilities we have there. And we just go to the next slide to look at one example. You can use this then to, for example, work out how you should ideally charge your electric vehicles. So the case here, the highlight is an artificial intelligence model-based optimization of this charging process, which not only takes into consideration the price of the electrical power, but also battery aging. And that has been implemented and tested in the Energy Lab, where we have charging stations for battery electric vehicles. And this is also done in collaboration with industry. Next one, please. And the last lab here in that part is the Power Hardware in the Loop lab. The idea here is that you put a hardware which is involved in the energy system, in the grid, in the microgrid. You put that in an environment where you connect it into a virtual grid, and then you provide via this virtual grid a certain situation, a certain voltage and frequency to this device. And then you measure the reaction of that device and feed it back into the model. And in that way, very quickly, in that way, you can study in a simulated grid the performance of the device under study. That's why it's called hardware in the loop. And this is very important to study the performance of critical components, also of other components in their integration in the grid. So next one, please. Now we move over to the chemical world, to the let's say process engineering part of the Energy Lab, and that's about sector coupling. What you see here is the blue part is the power side, and then the green part and the red part is the chemical and the heat side. And the orange part below is how these plants, how the data go into the Smart Energy System Simulation and Control Center. And what we have there is different electrolysis technologies. That's about in the middle, where you have the PEM electrolysis, that's the water electrolysis, and also the high temperature steam electrolysis. And the upper one is a variant of that. That's a co-electrolysis unit. There you can simultaneously electrolyze carbon dioxide and steam. So you get directly a synthesis gas out of that, and not only hydrogen. And with those gases, we go into our e-fuel synthesis plant or in a methanation plant. That's then the power to fuel and the power to gas approach. We get the CO2, wait a minute, just can you go back? We get the CO2 from a tank or from direct air capture, so from the atmosphere, and or from the biomass process chain nearby, that's the Bioleak process. So we can also look at these process combinations and study how good they really work. And on the right side, you see that we further develop this in additional projects where we look more on the CO2 capture part, also on ideas how we could do that in ventilation systems of buildings. And we look at whether and how we can do power to X conversions directly connected to offshore wind energy in an isolated grid configuration. And there we look not only on the fuels, but also on the chemicals like methanol and ammonia. So next slide, please. And this is the picture you saw already. Now it's labeled with the different units. So it's you have the same logic. Green parts is the gas and fuel side, blue is the power side, red is the heat side, and yellow or orange is the information and communication technology side. Next slide, please. For methanation, that's a photo of the methanation plant there. Unfortunately, the formulas are killed here, so you don't see the chemical symbols, but it's just the reaction equation for methanation. This is a plant where we validate new reactor technologies. That's the bubble column reactor system. The catalyst is suspended there in a liquid heat carrier, and that is very good to swallow, if you want, the fluctuations that you could have. If the electrolyzer sees different power, you get, of course, a different volumetric flow of hydrogen, and then this kind of reactor technology is very good for working with this intermittent conditions, and that can be validated here in this plant. Next slide, please. And this is now referring to the microstructured reactors we have developed over the years at our institute, and which we have then licensed out to our spin-off. I just briefly explained the principle. We basically have reactors where the catalyst is used as a thin layer of powder in between plates, which can be cooled very intensively, very effectively. And that allows us to reach much higher performance per volume and still control the temperature very well. And that was established first in these lab units here. And the table tells you that it works much better than conventional technology. And if we go to the next slide, you see that we did a scale up. We made these plates bigger. We built modules. We looked more in detail into the temperature profiles we get. We built up a technical system in the lab, still in the lab. We got more of those fuels and were able to characterize them regarding the application. And on the next slide, if you switch to the next slide, you see the status where we are now. We have modules in container plants. We have licensed this out to our own spin-off, which was created 5 years ago. It's Ineratec, and Ineratec has been doing very well so far. They have now 50 people, 50 employees, and they offer this kind of technology commercially on the market. And we see how this looks like. We see on the next slide. That's an actual picture of one of the two of their 1 megawatt PTL plants. That stands for power to liquid. This is in Werlte in the north of Germany. You may have seen that. And on the left side, you see a reactor there that generates synthesis gas. And on the right side, you see behind those people, you see also reactors. It's actually 8 of those reactors are in this container. And both steps together give this plant that converts CO2 and hydrogen into liquid hydrocarbons. And the scale is around 1 megawatt. That's where they stand now. And they also develop now a 10 megawatt plant in Frankfurt Höchst. Next slide, please. And we are interested in how we can have a very good heat integration in those power to X process chains. That's why we study a combination of those here in the Copernicus project, power to X. We combine direct air capture. That's where you take the CO2 out of the air. For that, you need a lot of energy. And we combine that with the high temperature electrolysis that has a very high energy efficiency. If you have already steam, then you do the steam electrolysis. With the third step is the Fischer-Tropsch synthesis. I mentioned that already. And the fourth step is the upgrading of this Fischer-Tropsch raw product to finished fuel. And if you combine that in the way that you use the waste heat from Fischer-Tropsch synthesis to provide the heat for the direct air capture and the high temperature electrolysis, you have a very good overall energy efficiency. And that's why we do that. And on the next slide, we see the status in that part. If we look on that picture on the right, you see an aerial view of the energy lab, which you already saw. And the other pictures are renderings of the direct air capture module and the co-electrolysis unit. The direct air capture module is in red and the co-electrolysis unit is in blue, which are now being built at the sites of our partners and which will be integrated in this Energy Lab site, which you see on the photo. And then we can demonstrate this process in the scale of about 250 kilowatt for the electrolysis. We will produce around 300 liters of fuel per day. And that's the syngas path. And in the Energy Lab, we can also do this simpler hydrogen path. That's on the left side of this picture, where we work with an existing PEM electrolyzer and a syngas generation via this reverse water gas shift reactor and then Fischer-Tropsch. And also with the version where we do steam electrolysis instead of water electrolysis. So then we can combine these different process chains regarding and evaluate them and judge them regarding practical operation, regarding dynamic capability, and also regarding overall energy efficiency. And then we go to the next slide. Yeah, that's already the point to tell you that we did quite a bit of public outreach to spread the word about Power-to-X, in particular also about these decentralized plants. And there's also a nice brochure for the Energy Lab, which you can download. And yeah, that brings me to the last slide, I believe, which is the conclusions or the outlook, if you want. So I hope that you have seen the capabilities we have with this Energy Lab. And for us, it's really a cornerstone in many projects. I could only highlight and mention the most important ones. And it's a really unique opportunity to validate new technologies. They're developed by us, but also developed by partners in a realistic system environment. And that holds for the electrical side, for the chemical side, and also for the ICT side. It's for Power-to-X, it's really a backbone infrastructure. It's modular. We can go there, remove containers, put there other plants, and study the performance of those processes then in this environment. And one area which we identified is the field of electrification of chemical processes. So more on electrolysis and electrosynthesis, so that we get even better efficiencies and less CO2 emissions. And also we put more focus on negative CO2 emission technologies. This is a complicated field, so the tasks are usually complex and interdisciplinary collaboration is required. We have not yet realized the full potential here between people from informatics, people from electrical engineering and chemical engineers, but we have made really good progress there. And the last point, I think climate change is really a serious issue which will push us hard in the coming years, both in research, because we have to be quick, we have to single out promising developments and push them towards application. And of course, also in industry and in society, that's, I'm convinced. With this, I would like to thank you for listening, and I'm certainly available to explain more in detail or to answer your questions. Thank you very much.
Yeah, thank you very much, Professor Dittmeyer. And I also want to encourage the audience to bring up some questions. And yes, we already received some questions and I would like to start with them. And it's like, when do you think, Professor Dittmeyer, when are e-fuels ready for market?
Technically, I mean, ready for market usually means the question, when will we have millions of tons available? That I think will take 10 years. Within 10 years, I can imagine that we could have first large plants running, which will then provide probably first kerosene in reasonable quantities. Technically, many of the things are ready. but on the side of the regulation and on the economic side, there are still challenges.
Okay, and one other question that came on was, are synthetic fuels cleaner than fossil fuels? And also regarding the application, can they be used in cars, like the cars we are driving right now?
Yeah, one of the advantages of those drop-in fuels, like I showed you based on Fischer-Tropsch, is that you can use it in the existing infrastructure, both for storage, distribution, but also the cars, the planes, the ships, etc. They normally burn cleaner because they have no sulfur. You make them out of CO2 and water, so they are relatively pure. And you can also optimize the composition in certain regions or in certain ranges. So they burn cleaner. Of course, they create CO2 when they are burned. And so if you want to be them CO2 neutral, you have to take the CO2 either from the atmosphere or from an unavoidable point source. Could be also, let's say, biomass, like biogas. You take the CO2 from there. So that you have to consider. So it's not only the, let's say, the typical particulate emissions and NOx, etc. It's also the question of CO2. But yes, you can use them in existing cars. And the question is how you regulate that, whether you want that or whether you don't want that.
So the regulation would be like a certain percentage in the that is content of the gasoline.
Yes, that's what we have in kerosene. We have a quota to be admixed, for example, 2% until 2030 in Germany has to be admixed as e-kerosene. And that's already something like 200,000 tons per year. For that, you would already need at least one bigger plant to synthesize. Okay. In the gasoline range, it's a discussion whether you want to allow that or not, because there you have the alternative of battery electric vehicles, whereas in big planes that go for long distance, you don't really have an alternative right now to kerosene. So that's why the regulation has an important role there. Technically, you can say that when you produce kerosene, you always also produce some other hydrocarbons that could be used as diesel, for example, for trucks or for ships, or the gasoline part could be used in cars. The question then is whether you want that. If you don't want that to be used in cars, there is also the opportunity to use that as a feedstock for chemical industry. So that's why regulation is important here.
Okay, so and we also had some questions coming in, and I would like to read this out loud. So is there any research with liquefied high pressure air as energy storage in the energy lab?
No, we don't do that. Compressed air storage, I think that's what the question is about, is one of the, let's say, technically established units, but you said liquefied air. Okay,
yeah, it was liquefied and or high pressure air, as energy storage.
High pressure air, that's what I mentioned. Compressed air storage is, let's say, state of the art, not used much, but in principle possible. I also know that liquefaction can be is done by Linde with that context, but we don't do that in the energy lab.
Okay, is it done in KIT with some like for example with Linde gas or so in cooperation?
Not that I am aware of. What we do is liquid hydrogen. We do a lot in liquid hydrogen, also new infrastructure. That's done at ITEP, Institute for Technical Physics. Tabea Arndt, Matthias Noe are doing that, also with an eye on combining liquid hydrogen transport with superconductivity. So with transport of electricity in that cold state, you can have very efficient energy transport if you combine the two. And you can also develop interesting applications based on this technology. It may sound a bit futuristic, but we also do long-term research that might find a way into application in a few decades.
Okay.
So on liquefaction of air, I mean, I don't know everything in KIT, but I'm not aware of.
Okay, thank you very much. Yeah, and now we have another question regarding towards more industry, like also Ineratec was here mentioned as such a successful startup. Can you please guide us on which companies to aim for, where there can be done internship or work student positions in the field of energy engineering domain in and around Karlsruhe? So it's now your chance. If you are looking or your team is looking for a work student, then here is one.
Yeah, well, of course, we can offer the possibility to do something. I'm pretty sure that Ineratec also welcomes people, also students. They also always actively look for people they can recruit. So I guess this opportunity will be there also in Ineratec. But of course, you have to approach them. You have to ask them.
Yeah. Would you name some other companies you would think of? They could be approached.
Yeah, well, of course, there is Siemens, of course, but we with this field are more connected to Siemens Energy in Erlangen. So locally in Karlsruhe, well, there's ENBW. They are partnering with us in this offshore Power-to-X project. There will certainly, I guess, also be some opportunities. Yeah, maybe if there's really a person interested in this, should send me an email. I try to think about it more in detail and would reply then directly.
Okay, yeah, thank you very much. And I also want to mention to people from industry here in the session tonight. So if you are looking for student assistance or work student, you can also approach me, as I'm also in touch with our energy engineering and management participants, and they are also interested in gaining industrial experience and already sharing their know-how. So then we also have a question that is, are you conducting business research connected to the energy lab?
Well, we only, let's say, do feasibility. It's more technical feasibility. We also do some economic studies, but not really business research. We do that usually together with colleagues at Campus South, Wolf Fichtner, for example, or with the with ITAS, people from ITAS, and yeah, so that's not our main. We develop the technology. We try to bridge this gap between the lab and, let's say, the practical application. We also actively support these spin-offs and startups, also companies like Sunfire, Climeworks, via research collaboration, and but not really to business research.
Yeah, there I would just like to mention the ITAS, that's the Institute for Sustainability here at KIT, and also worldwide very highly renowned as one of the first sustainability institutes, just to add this on here. And there maybe I would think at the Sensic, is there also research done in the field of information? Are maybe projects that could also be in a business IT aspect maybe be utilized?
Yes. Yeah.
Okay. So, and then we have another question from a PhD candidate who is focusing on the circular economy at Schaeffler Automotive in Bühl. And he's asking, is expeding the let's make this mainstream process truly a question of demand or the infrastructure for supply?
I didn't get that. Can you repeat?
So I'm going to read it again. Is the repeating the let's make this mainstream in process truly a question of demand or the infrastructure for supply?
I still don't really get the question. I mean, is to what does it refer to? The CO2 reduction or to the circular economy?
Yeah, I think in the field of energy, we often have this, that infrastructure, of course, is always an issue that is discussed very broadly. And then, of course, also the demand usually stirs the market. So, but maybe I can ask Shaikiran again to drop me a note, and I'm going to move on to the next question. And here we have, are you in need of more sophisticated or more cost-effective gas and liquid measurement systems?
We are always interested in better measurement technologies and cheaper measurement technologies, but that's probably a question that has a commercial background. So I can say that for these decentralized, containerized plants or modular plants, they don't necessarily have to be container sized, but they are modular. So it's smaller capacity plants. The cost of the whole plant is important. So if you can lower that by having something to offer that is good for that, I suggest that you approach Ineratec. I'm quite sure they are always screening the market and they are interested in improvements that you might be able to offer there.
Okay, and then the next question, what's more efficient in your opinion, to feed the offshore generated energy into our electricity grid, which needs an expensive upgrading for the South-North lines? Or is it more efficient to use the power to gas process and feed the methanized gas into existing gas pipeline system?
Yeah, that's not so easy to answer. Probably there are studies around for that. I mean, the general problem is quite similar. You can over-dimension a grid so that it will be able to distribute very high power at times, but then most often it's running under capacity, so you have to pay for that. You can also do that with the gas then. So usually the transport of chemical energy is more efficient than the transport of electrical energy, at least over long distance. And that's why, that's one reason why this offshore power to X is also interesting. But the question probably assumes that you would, of course, connect the offshore wind park to the grid. What we are studying in this project is whether you can avoid that. Because if you can avoid that, you can go to locations even further out in the sea, where it's more difficult, even more difficult to connect that to the grid. And you would just produce the hydrogen there, or even better, produce something like methanol there, which can be very easily transported. But then the question is, how can you run a chemical plant like methanol synthesis with electrolysis combined, directly connected to the wind energy plant in a difficult environment such as offshore? That's the development target. But it's an economic incentive to reduce, to maximize the power, because the availability of renewable power is much better offshore. So you get almost 4,000 or 5,000 full load hours, whereas on land you don't have that. And so this is the situation which you have to analyze and then come to the conclusion, what is the optimal way in terms of energy harvested and then in terms of energy distributed. But it's no easy answer. At least I cannot say, okay, gas is better than power transmission line.
Yeah, this probably would be a session by itself, or maybe for a whole course here to discuss all the aspects there, influence there. But still, I know the participants value very much your opinion on that. And I would like to continue with to read out another comment or question. Is it common sense that the PTL is more sustainable? To bring this out on a larger scale, we are waiting for the customer demand to increase, or are investments already flowing into set up the infrastructure, preparing to push the supplies into the market?
Well, I think for kerosene, there is a big demand because, as I said, there is a quota already, and people have understood that the only way to defossilize aviation is within a reasonable time is to go to e-kerosene. And if you consider that today, I think the world consumption of kerosene is 1 million tons per day. So that gives 400 million tons per year, or 350 million tons per year. That's a huge amount of kerosene. So that the demand is there, it's very high. However, the cost is too high, still too high. You can easily calculate or convince yourself that 1 cent per kilowatt hour of power price translates into about 20 cents per liter of whether it's kerosene or diesel, doesn't matter. So 1 cent per kilowatt hour gives 20 cents per liter. Now, the market price for kerosene is about 50 cents per liter. It's not taxed. So that means you can allow for 2.5 cents per kilowatt hour power price, and then you already have 50 cents per liter. And there is no plant, this is only electricity. You also need CO2, you need the plant, you need transport, you will have losses. So that tells you that economically, if you compare it to fossil products, it doesn't work. I mean, this is common sense. You need regulation, you need CO2 taxation in order to generate a viable business case. And that's what I observe. This is going on. And I'm very convinced that it will move in this direction.
Yes, so this is what we then also get in the comment. Yes, so it naturally goes back to the question of regulations. Yes, so this is now where politics comes in, and where they have to make the market more fair. Yeah.
Well, we should not forget that when you discuss costs, the market can do that, but you have to tell the market. You have to introduce the penalty somehow. What will happen if we don't reduce the CO2 emissions? If we fail to reduce them, we will pay costs in different other fields. And that is not priced in so far. And that's why the market alone will not provide the solution here, in my opinion. That's why you need this regulation. Or we can factor that in, but I don't see how you can factor that in the climate change costs.
Yes, this will be a very difficult issue also if now it first goes through media that breathing illnesses or asthma might be caused with climate change. So if those costs now come on top, this is really a huge scenario of what all has to be taken into account and be also put down into what needs to be paid for. Yeah. So I'm checking the questions, and I have one more that is a bit more technical. So what is the difference of the process you are using in comparison to the known Fischer-Tropsch method?
Yeah, that's easy to answer. Basically, we develop these micro reactors that I showed you, which have the advantage that let's say they can get the most out of a very good catalyst. So if you have a very good catalyst and you put it into that reactor, you get very high performance. High performance means you don't produce or you produce less undesired methane, because this is the side product which you produce when you don't control the temperature well. So that's one argument, one advantage, better selectivity. And the other advantage is much better productivity per unit of reactor volume. So you can make the reactors, let's say 100 times smaller, and still they have the same capacity. That's maybe not important in some applications, but it's important when you want to do that in decentralized plants. So when you don't have the very big plants, but the idea is that you would have a power-to-X plant that can work with transient mode, that you can ramp it up, ramp it down relatively fast. This is not possible with conventional technology. So that's where we make the distinction.
Okay, thank you very much. And then I'm moving towards the end of the question. And I would like to read this question out to you. To speed up the green energy change, many people are speaking again about nuclear energy. What is your opinion? Could this energy again be an important player in the war against emissions? Or do you think the risk is still too high?
Yeah, well, if I'm not a specialist in nuclear energy, if I look at the price of electricity these days via photovoltaics and wind energy, and the cost of nuclear power plants, and how long it takes to get permission to build one, then I would say that nuclear power is not the way to go. It takes too long, it's too costly. The long-term storage is not really solved. Politically also not. I don't see a big advantage of that. I know that in other countries, they look at it different. For example, France, but also in France, there is a certain move to renewables. And if you consider that with wind energy and photovoltaics, you have regions in the world where you can really, for low price, produce a lot of renewable power, that would be my favorite. So to do that in partnership with such countries, where you also help to develop those countries, and then to import, let's say, a chemical energy carrier based on that. I think that is, in my opinion, the better solution compared to nuclear.
Okay. So yeah, thank you. And then I have also, beforehand, I got approached regarding the master here at HECTOR School. And it was the question, how would I know if I can be accepted in the energy master? So therefore, I would ask you to get in touch with me afterwards, and maybe drop your CV or just a short introduction about yourself, what you have been doing in your bachelor's. Work experience is very important to be accepted in this master. And then I can quickly give you a feedback about how the chances would be to be accepted here in this master. Yeah. So, okay. And yeah, my colleague already also sent in my email, so please feel free to get there in touch with me. So yeah, thank you very much for all the participants, and especially Professor Dittmeyer. We will send out the slides, so it's also possible to go over them afterwards and have some thoughts regarding the energy lab here at KIT today. And yeah, I want to say I'm really convinced that this ecological change also offers a lot of opportunities for us, and I really hope we will be able to make a win-win-win for all of us out of this. And yeah, thank you everybody for participating, and please all stay healthy. Thank you and bye-bye.
Thank you very much. Bye-bye.